Pretty much everything you do, from boiling a kettle to, well, just being alive, it's all governed by just a handful of universal rules. We're talking about the laws of thermodynamics, and today we're going to break down exactly how they shape our world. We'll start with a simple question.
Okay, so picture this. You reach into your freezer. You grab a metal ice tray with one hand and, say, a plastic container of frozen veggies with the other. Now they've both been sitting there for hours, right? So they are the exact same temperature. But why in the world does that metal feel so much colder? Well, here's the secret. Your hand is actually a terrible thermometer. What you're feeling isn't temperature itself. Nope, you're feeling the rate, the speed at which heat is being ripped away from your skin. And metal? It's like a superhighway for heat, pulling it away super fast. That's why it feels so intensely cold. So this little gap between what we feel and what's actually real, that's exactly why we need a proper scientific way to define temperature. So, to solve our freezer puzzle and really to build any kind of reliable thermometer, we've got to start at the very beginning. The first principle of heat exchange. It's called the Zeroth Law of Thermodynamics, or you might hear it called the Law of Equilibrium.
The whole idea here is something called thermal equilibrium. It's pretty intuitive, actually. Imagine you pour some cold milk into a hot cup of coffee. What happens? Well, the coffee cools down, the milk warms up, and after a little while, they hit this single, uniform temperature. That's it. That's thermal equilibrium. At that point, there's no more heat flowing back and forth between them. Okay, so how does this help us measure anything? Well, let's break it down. Let's say we take a thermometer. We'll call it Object C, and we put it in contact with your body, which we'll call Object A. We just wait a minute until the heat stops flowing and that little red line stops moving. At that point, they've reached thermal equilibrium. All right, next step. We take that very same thermometer, Object C, and we pop it into a glass of water, that's Object B, and again, we wait for everything to settle down and reach equilibrium. And just for the sake of argument, let's say the thermometer shows the exact same reading it did before. And here is the beautifully simple but incredibly powerful logic of the Zeroth Law. If your body is the same temperature as the thermometer, and the water is also the same temperature as the thermometer, well then your body and the water have to be the same temperature as each other. It's just simple logic. If A equals C and B equals C, then A has to equal B. This is the fundamental idea that makes every single thermometer work. It's that simple. And once you know what to look for, you see this law in action absolutely everywhere. It's why your hot coffee eventually cools down to match the room's temperature. It's why a metal spoon you leave in hot soup gets just as hot as the soup itself. The universe is just constantly trying to reach this state of balance. Okay, so the Zeroth Law gives us a solid definition of what temperature is. But what happens when we change that temperature? Well, it turns out that heating things up doesn't just make them hotter, it actually makes them bigger. And this is a phenomenon called thermal expansion. And get this number right here, 12 centimeters, that is how much taller the Eiffel Tower can grow on a really hot summer day. I'm not kidding. As thousands of tons of iron heat up, all those little atoms start vibrating like crazy, pushing each other apart, and the whole structure literally expands and grows. That's the power of thermal expansion in the real world. And this expansion isn't just about getting taller, it actually happens in every dimension. So a railway track gets longer. We call that linear expansion. A flat sheet of metal gets wider and longer. That's area expansion. And a balloon filled with air swells up in all directions. That's volume expansion. Pretty much every material responds to heat in one of these three ways. All right, so all this talk about heat flow and things expanding, it brings us to the big one. Where does all this energy actually come from and where does it go? The answer is governed by the first law of thermodynamics, which is basically the universe's ultimate rule for energy bookkeeping. Now, the law itself is stated very simply, and I'm sure you've heard this one before. Energy cannot be created or destroyed. It can only be transformed from one form to another. You might also know it as the law of conservation of energy. And honestly, it's one of the most fundamental, rock-solid rules in all of physics. In the world of physics, we track all this with a really simple equation. Delta U equals Q minus W. Okay, let's break that down real quick. Delta U is just the change in a system's internal energy. Think of it as all the jiggling and vibrating energy of its atoms. Q is the heat you add to it, like when you put a pot of water on the stove. And W is the work the system does, like when the steam from that pot is strong enough to push the lid up.
Now, the key here, and it can be a little tricky, is getting the plus and minus signs right. It's all about direction. If you add heat to a system, Q is positive. If heat leaves the system, Q is negative. Simple enough. Now for work. If the system itself does work, like that expanding steam pushing a piston, W is positive. But if you do work on the system, say you compress a gas, then W is negative. It's all just about tracking where the energy is flowing.
Let's go back to boiling a kettle. Think about it. First, electrical energy flows into that heating coil, where it transforms into heat. That heat, that's our positive Q, gets pumped into the water, cranking up its internal energy. Finally, that boiling water creates steam that expands and forces its way out the spout. That's the system doing work. That's our W. See? The energy was never lost, not for a second. It just changed hats, going from electrical to thermal to mechanical. So let's just do a quick recap of what we've covered. First, we have the Zeroth Law, which gives us a solid definition for temperature based on the idea of equilibrium. Then we saw how changing that temperature makes things physically expand or contract. And finally, the big one, the first law, which gives us the golden rule. Energy is always conserved. It just gets moved around on the universe's great big balance sheet.
Which, leaves us with one final, really fascinating question. If energy is always conserved and can't be destroyed, then where does it all go? I mean, think about it. Every time we burn fuel or use electricity or do any kind of work, that energy transforms. But what does it transform into? And why can't we just get it all back and use it again? Well, that's a question that leads us straight into the second law of thermodynamics. But we're going to have to save that one for another day.